Hey everyone, thanks for tuning in to the first Polaris webinar. I'm Johnny from the Polaris team, and I'm happy to just kick off today's session by providing a quick overview of Polaris and what it is that we're focused on. So Polaris is a benchmarking platform that currently hosts hundreds of ML-ready data sets and benchmarks for drug discovery. And all of these are easily accessible through a simple and intuitive API. And so really our mission at Polaris is to improve the current state of benchmarking so that a lot of the methods and machine learning models that we're developing as a field can have more real world impact in drug discovery programs. And we know part of what makes benchmarking so difficult in this space is this lack of standardized benchmarks or guidelines around method evaluation, comparison, and data set curation. And so that's why, starting with a focus on small molecule predictive modeling tasks, we formed a steering committee comprised of industry experts to collectively craft such guidelines for the community. And so today I'm really excited to introduce a member of the steering committee, Jeremy Ash, who's a senior scientist at Johnson & Johnson. And he was the first author on our recent guideline paper for method comparison. And in today's webinar, he'll be diving through this work. Let's get into it.
Okay, so I'm going to try to do this without video at first because there's computer's been laggy for some reason, but um, I might try to turn it on in a little bit if it becomes more stable. So thanks for the introduction, Johnny. Like you said, I'm on those Polaris Small Molecule Steering Committee, and I'm going to be talking about our recent preprint called Practically Significant Method Comparison Protocols for Machine Learning and Small Molecule Drug Discovery. And I wanted to preface by saying that the paper is intended to be a beginner-friendly set of guidelines for method comparison, and we tried to propose a workflow that would be accessible to beginners and that we could explain in enough detail where we were confident everyone would have a good understanding. So this talk is going to be somewhat at a beginner level here. First, I'm going to give a quick introduction on how models are benchmarked in drug discovery. In drug discovery, we're performing expensive and time-consuming experiments to profile molecules and get insight into their therapeutic potential. ML models are trained on historical data to serve as surrogates for experiments. And the models need to be performant because they're being used to make costly decisions about deciding what compounds to make or what experiments to prioritize. And as in any other ML field, we're often benchmarking models and determining the most performant methods. I have two examples here to give some context on the type of benchmarks that are typically performed. When proposing a new method in literature, it's important to contextualize results and compare to a simple baseline and the current state of the art. When deploying a model in industry, we often have established methods that are already in production. In order for us to justify the investment in a new model, and mute this person, in order to justify the investment to a new model, we need to demonstrate a substantial improvement over the existing method. And there is also a larger role for benchmarking than just ranking models. Benchmarks can motivate research directions by defining a problem for the community to work on. So they don't just measure performance, but they're also steering the community to an extent. And before I go into the current paper, I wanted to point out that we had an earlier publication from the Polaris Steering Committee. This was a letter to Nature Machine Intelligence where we announced the initiative to improve benchmarking, and letter was meant as a call to action for the community. And we discussed common challenges in benchmarking and emphasized the importance of a cross-industry collaboration. At the end of the letter, we propose three main pillars to address the challenges with benchmarking. The first is a recommended set of data sets that represent tasks typically performed in drug discovery. The second is a set of guidelines for dataset curation, method evaluation, such as dataset splitting or evaluation metrics, and method comparison, such as statistical testing. The third is a set of open source software tools to simplify the adoption of best practices. So the talk is going to cover some of pillar 2. We'll talk about the method comparison and also evaluation metrics. And then we'll also talk about some open source tools that we've been developing. Okay, so this is the current publication. This is a paper now in Kim Archive, and we're taking open comment on the paper for a couple months. So to get input from the community, and then we plan to submit this to a journal for publication, and I'll talk more about that later. So to help motivate the paper, I'll start by discussing why replicability of ML research is important. For research to progress efficiently, it's important that we follow good scientific principles. And one central principle is the replicability of results. You're not able to build off of others' results if you can't replicate them. And without replicability, research directions can be pursued under bad assumptions. So specifically for methods comparison, if a method is claimed to be superior to the state of the art on a benchmark, we expect the result to be replicated on similarly generated data sets. Unfortunately, much of ML research is not replicable. And below here, I have some high-profile papers from the last couple years demonstrating that there are replicability problems across a wide range of ML fields. The first papers cover many fields. First 2 papers here, they cover biology and chemistry, but also modern fields like computer vision and natural language processing. This second paper here is focused on statistical replicability, which is something that we go into depth in our paper as well. And it's important to note that the drug discovery data sets are particularly at risk for replicability problems, and that's because they are classically smaller, imbalanced, and noisy. They're also heterogeneous, which means they're cobbled together from many different sources, for example, labs with different protocols. So this table shows what people are typically doing in drug discovery right now. And we're tired of seeing this bold table. So the bold table shows the average metric for each model under k-fold cross-validation with different tasks on the columns. The model with the best value for a particular task is shown in bold. These best models only have their other models without bold that are only slightly worse performance than the bolded models here, though. So after considering uncertainty in performance metrics, it's unclear whether there really is a difference here or if these are just the best performing models by chance. The problem with comparing metrics calculated from cross-validation folds is that we're actually comparing distributions, and when we compare distributions, we need to look at more than just the mean. So I have a definition of statistical replicability here, the ability of a result to hold under resampled conditions that should not affect the claimed result. For example, different random seeds or different trained test splits. If there's a real systematic improvement of one method over another, it should be seen consistently under this resampling. And the way that we establish replicability for methods comparison is through statistical tests. And it's important to note here that statistical tests are not the only thing necessary to guarantee replicability, but the reason why we believe they're important here is that they can already eliminate many false positives. And they also can be implemented using methods that are well established and with well worked out theory. So we are demonstrating a concept on the right here. It shows the distribution of performance across CV folds for models built using two fingerprint types. So sort slice and Morgan count. The box plots show distribution of metrics, and edges here connect points from the same cross-validation fold. Edges are green when sort slice outperforms Morgan count, red when Morgan count outperforms sort slice. The majority of splits have sort slice as the best performer, but there are several splits where Morgan count is better. So it's unclear if the better performance suggested by the mean here is actually reliable enough to say sort slice is really the better model. For drug discovery, it's important to perform statistical testing, but it's currently not common practice. There are many factors that we see limiting the usage of statistical tests. First, there are few user-friendly tools for this type of analysis. Next, the machine learning researchers often lack the statistical knowledge to perform this analysis. There are some pitfalls when doing statistical testing that we'll point out, which can make this challenging. And then next, replicability could be incentivized more by researchers and institutions. In our paper, we're trying to address some of this by providing a clear set of guidelines. We also provide annotated examples in the paper and more on GitHub. We also provide our code that uses open source software. Should be straightforward for others to repurpose. So I think we're gonna, Johnny, what are we doing about questions? So Ramil has his hand up here, but are we gonna take him at the end?
Yeah, let's save them for the end. Unless Ramil, is it just like a
I
quick
did
clarifying
nothing,
question?
sorry, but somehow it's open. No, it's some misclick.
Oh, okay.
Oh, okay. No
All right.
worries.
Yeah. So I think we're going to take
Thanks.
questions at the end.
Yeah.
Okay, so here's an overview of the guidelines. I'll go into more depth on how these were derived, but first I wanted to give an overview and see if anyone had feedback at a high level. And if I think one thing we could do here is have people add questions to the chat, and we can get to those at the end if Johnny wants to help curate those. So the guidelines are summarized in a decision tree. The path in blue applies to most use cases, and exceptional cases are shown as well. The first guideline is on estimating the performance sampling distribution. So we recommend using a 5x5 repeated cross-validation if you can. So that's 5 repeats of 5-fold CV. The procedure should work well for typical data set sizes. However, if your data set is small, then less than 500, then it will be better to perform 5x2 CV. If your data set is very large, then statistical testing is unlikely necessary. The 500 threshold is based on the literature, but the 100K threshold is just based on what we thought would be the upper limit on what is computationally feasible. The next guideline here is on statistical testing. So we recommend the Tukey honestly significant difference test for pairwise comparisons. The assumption should be reasonably met in most cases, but if they're strongly violated, we provide an alternate non-parametric procedure. The next guideline is on determining practical significance. So when reporting a significant difference between methods, we also recommend providing an explanation of how the result is practically significant. And we recommend using metrics that are motivated by the ultimate use case of the model. And then the last guideline is on visualization and interpretation of results. We recommend an extension to the sign plot. This includes statistical significance and effect size in a single plot. And we also recommend an additional plot in the supplementary that provides confidence intervals for effect size of pairwise comparisons. And then we have a disclaimer here that is the statistical testing procedure here is not a cookbook. There are valid reasons to deviate from the guidelines. And so these won't be perfect for every scenario. And we're definitely still open to feedback here. But if you do decide to deviate, then just be transparent about what you're doing. Okay. So the first step in the guidelines is to determine how to sample from a performance sampling distribution. And here are a couple of options and our recommendation on what to use. We recommend against a single split for assessment. So often people are trying many modeling attempts, such as different methods or architectures. And with many attempts, you're likely to find a configuration whose performance looks good by chance on a single split. But that will be overly optimistic and dependent on that particular split. If you split differently, you would likely see worse performance. So to avoid this, it's important to do an analysis across multiple splits. So one approach that does multiple splits that we recommend against is this vanilla cross-validation. This is just k-fold CV. For this type of CV, there's substantial overlap in the training sets across replicates. So this introduces correlation between metrics for each replicate. And the problem is that the correlation violates the independence assumption of statistical tests, and that results in frequent false positives. So that's been well studied in the literature. I have some prominent papers here at the bottom. And so repeated CV has been proposed as a straightforward way of resolving this. This leads to statistical tests that are more reliable. And repeated CV is simply repeating k-fold CV with different random seeds for the splits. So we get different splits each time. We use the same splits for each method when comparing so that there is a fair comparison. And the figure here is showing 5 repeats of twofold cross-validation. And then I'm also showing nested CV here to distinguish this from repeated CV. So often nested CV is recommended for hyperparameter optimization, but here repeated CV is better for statistical testing. So what we're recommending ultimately is using 5x5 repeated CV for general use, and this is how we came up with that guidance. So Thomas Dieterich showed in the 90s he could derive a statistical test with good properties using 5 repeats of twofold CV. There was also some follow-up simulations done by Yasuo Bingio, which is down here. And unfortunately, this guidance is now out of date because it was derived for small data sets that were typical at the time. So for larger data sets, 5x2 will lead to an overly conservative test and poor estimate of performance because you're only using twofold cross-validation. And this was addressed in a recent paper by Bates et al., and they derive a nested CV procedure that provides a more accurate estimate of performance variance. Unfortunately, the method is computationally expensive, too expensive for most applications, and it also limits the performance metrics you can use. So we performed an experiment where we compared a variety of CV procedures against the Bates method on a representative data set for drug discovery. We found that 5x5 CV had good performance and is easier to generalize to various use cases. So basically the intuition here is that larger data sets can accommodate 5 folds instead of 2 folds and still have sufficient independence of samples. The 25 samples you get from 5x5 give you enough samples to perform a proper statistical test. And we also have an upcoming paper with more discussion on splitting methods to use for cross-validation. That's the next publication that's planned here. So other considerations we mentioned in the paper for cross-validation, your splitting should follow best practices. So you should minimize splitting of close chemical analogs across splits to avoid over-optimistic performance estimate. Scaffold splits or chemical structure clustering are common to avoid this. Most splitting methods are compatible with repeated CV. There's no formal requirement that the fold should be equally sized, but you should try to avoid dramatic size differences to perform a reasonable CV. And but we mostly chose not to provide guidance on the splitting methods and to save that for the upcoming paper. And then for hyperparameter optimization, often people will want to tune hyperparameters when performing a repeated CV. If you do this, then split the holdout fold into test and validation and use the validation set to tune hyperparameters. And so we recommend that approach over doing a full nested CV. So the next step in the guidelines is on choosing statistical tests for the difference between methods. So we tried to pick tests where we could convey a good understanding to readers without a need for much stats background. And in the appendix, we discussed the tests in details, their underlying assumptions, and how they relate to CVs so that people can understand the tests they're applying. So I'm going to walk you through this figure here. The procedure for a t-test for the difference between two methods is shown. And if you assume the null hypothesis is true, then the mean for two methods are equal, and the t-statistics will have this distribution shown. Then the t-statistics that actually observed in the data is compared to this distribution. And the t-statistic is just the difference between the difference of mean performance between methods normalized by the standard deviation. And the p-value is the probability of observing this t-statistic as extreme or more extreme than what is observed. And the significance level is the probability of false positives that is considered acceptable. So the level determines the threshold and the p-value that's required for significance. If you set a 0.05 level, that means you expect to see 5% false positives or less with the test. So in the example, the result is not statistically significant because the p-value here is larger than the alpha level. And controlling false positive rate is the most important thing when comparing methods, because when we claim statistical significance, that gives people certainty that the result is meaningful. We want to make sure we're not giving people an inflated sense of certainty. And then after false positive rate, statistical power is also important, and that's the probability that a difference between methods will be detected if one really exists. So the test we propose is this two-key HSD, which is an extension of the t-test for all pairwise comparisons. And that's typically what we're doing in method comparisons. Two-key HSD makes a number of assumptions. Fortunately, the assumptions have been well studied, and the test is known to be highly robust in this repeated CV context. If the assumptions are strongly violated, then we recommend a non-parametric test that should work well in this scenario as well. And then correction for multiple testing is necessary. So all pairwise comparisons are performed, and this quickly becomes a lot of tests when many methods are compared. So correction for multiple testing controls the false positive rate. And so two-key HSD already performs a correction, and for non-parametric, we recommend Bonferroni. Okay, so the next step in the guidelines is to determine practical significance. In drug discovery, practical significance comes down to whether a new method improves a scientist's decision-making. In this figure, we assume we're trying to prioritize compounds with good solubility for synthesis. A typical threshold is greater than 100 micromolar. We've run statistical tests and found statistically significant differences in mean absolute error, MSE, and R squared between light GBM and chemprop. But if you look at the metrics in the plot, there's only marginal differences between methods. So is the effect size large enough to be meaningful? And practical significance is a statistical term that means is a statistical significant difference large enough to be meaningful in practice. And to get an understanding of this, we use this post hoc classification here with the 100 micromolar threshold and measure performance in terms of precision and recall. We observe that the precision stays more or less constant across methods, but recall is substantially lower for light GBM. This is actually a 17% increase in recall for chemprop. So that means if you were to use this model as a filter, chemprop would identify 17% more molecules with good solubility. That would have a real practical impact on drug discovery programs. So this is just an example of how you could demonstrate practical significance with these results. So in the appendix, we have a set of recommended metrics for evaluating performance in different modes. So regression, classification, and ranking. For regression, we recommend Pearson R squared to evaluate correlation. We also recommend mean absolute error, RMSE, to capture how far predictions deviate from true values on average. We also recommend a percentile absolute error option as well. That will give stronger guarantees on performance. For classification, it's important to keep in mind that data sets in drug discovery are often highly imbalanced. So we recommend metrics that handle that imbalance well. We recommend Matthews correlation coefficient, which balances positive and negative classes. That's useful if you place equal importance on the classes. The area under the curve metrics are useful because they evaluate performance over a range of thresholds that may be used in practice. So area under the ROC curve is useful when you care about classes equally. Area under the PR curve is useful when you only care about the positive class. So like in virtual screening or deciding what compounds to make. While AUCs are useful summaries, it can be difficult to determine whether a difference is practically significant. So is a 0.05 difference in AU ROC actually meaningful? So to assess decisional impact like that, it's useful to pick representative thresholds like we did in the previous example and report metrics at those thresholds. And then with ranking, the ranking metrics are useful to provide additional granularity beyond classification and give a sense of the rank order relationship between compounds. Both Spearman's rho and Kindle's tau are useful metrics. And then we have recommended modes for the different types of models. So for regression models, we recommend both regression and ranking mode, and classification if your regression performance is suboptimal and you have a sensible threshold. For classification models, we recommend evaluating as classification and then ranking if additional granularity is desired. And then because the decisional metrics are useful for determining practical significance, I wanted to provide a couple of additional examples. First, for property models, we're often using them to decide what compounds to make. And here the task is to filter a large set of compounds such that the result has a high fraction of good compounds. And the set should be as large as possible to provide diversity for design. So for solubility, this would be requiring predicted solubility greater than some threshold, so the right-hand side of this plot. And a decisional metric in this case could be to decide on a minimum acceptable precision, so 75%, for example, then select a threshold with the largest recall that meets this criteria. So that's called recall at precision in the ML literature. And the example on the right, we just used a 100 micromolar threshold to keep things simple, but that this metric is how you would tune that threshold. Then the next example is deciding what compounds to not make, which is also a typical task. And here we're trying to eliminate a large number of bad compounds while eliminating as few positives as possible. So for solubility, you'd filter out low predictions. And a decisional metric in this case would be to set minimum acceptable recalls, so 90 of the positive class, so 90%, for example, and then select a threshold with the maximum true negative rate subject to that constraint. So that would be true negative rate at recall. Okay, are we on time? So the correlation and error metrics are influenced by the dynamic range of the data. It's generally easier to model a data set with a large dynamic range. This is important to be mindful of because benchmarking data sets can have a larger dynamic range than what we see in practice in drug discovery, and this can lead to overly optimistic performance. So here we have a Delaney solubility data set in the molecule net benchmark. The data set spans 13 log units, but in drug discovery, we typically focus on a much narrower threefold range. We show the Pearson R squared for both scenarios. So for the 13-fold range, there appears to be a high correlation. It's because the signal to noise ratio is very high. But for the threefold range, the signal to noise ratio is much lower, and the correlation metric is half of what it would have been estimated with the benchmark. So be mindful of the dynamic range of your data, and your benchmark should at least ballpark match your application. Okay, next, it's important to put model performance in context by estimating lower and upper performance limits. So a lower limit is necessary because metrics can be misleading based on the underlying data distribution, and you may not be doing much better than a simple baseline if you're not careful. Some examples of simple baselines are a model that simply predicts the majority class for classification, or a model that predicts training set mean of the response for regression. And then an upper limit estimate is useful because it indicates optimal performance you should expect to see after considering the experimental variability of the assay. So if your performance is better than the variability of the assay, then something's wrong with your evaluation. For example, with IC50, a typical variability is 0.3 log units. So your model performance can't be better than that. And we have an algorithm here for estimating the upper limit from a paper by Brown et al. So the last step in the guidelines is to visualize and interpret the results. This first plot we're recommending is an extension to a plot called the sign plot in scikit postdocs package in Python. The original plot showed a heat map of all pairwise p-values. And we call our extension a multiple comparison similarity plot. Plot colors by the average difference in performance between methods. And each cell in the heat map also has a star annotation that indicates the level of significance. So, and then we have a numeric difference in the cells, but that can be suppressed if there's a large number of comparisons. And then on the margins, we have the performance for individual models. And that's important because that information is lost when you just look at a difference, but it's important to understand the utility of the individual models. And to simplify the interpretation, the plot sorts methods on rows and columns by their average performance, and the top left block of methods without statistically significant differences are all plausible top performers. So for precision, we have no practically significant difference, even though there is a statistically significant difference here. And then for recall, there's clearly a practically significant difference between models. Okay, so another figure we recommend conveys confidence intervals of the difference between methods. This is common practice for the interpretation of these tests. In the plots, if the interval does not cross the 0 vertical line, then there is a significant difference. The Tukey HSD can be used to construct these intervals, but that's not possible with the non-parametric method. So it's useful for the readers to know the range of possible performance instead of just an estimate. And so a point estimate of the difference can appear substantial, but if the associated interval is large, then the result may be less meaningful. And so the problem with these plots, though, is that there's a number of pairwise comparisons often. So these plots can get difficult to visualize, especially if you have multiple metrics. So we recommend putting these in the supplementary, either as a plot or tabular form. So this doesn't need to be a main figure, but it's helpful for the reader to be able to look this information up. So I'm going to go a little bit faster here to make sure I get questions in. But we have code on GitHub. We have a number of workflows demonstrating both the example in the paper and then other examples of classification and non-parametric testing. Pat created a GitHub repo called ML Benchmark, which our repo uses for repeated cross-validation that can flexibly accommodate modeling methods. It only requires that you create a wrapper class for the model and a validate method. So it's pretty easy to extend. This is what we have next for the group. So we have this open feedback period. We plan to submit to JSIM in February 2025. Polaris has plans to extend their current leaderboard to more information-rich dashboard, which will incorporate some of these guidelines. So the Polaris platform is one way we're trying to go beyond these papers and make adoption of the guidelines easier. And then here's a link here for the open comment discussion forum if you want to leave feedback. And then last acknowledgements, I'd like to acknowledge the Polaris Steering Committee, which has provided us with a lot of helpful feedback on the guidance along the way. And then thanks to Valence Labs and Johnny here for hosting this. And okay, I think we've got 15 minutes for questions, so that should be good. Thanks, everyone. Let's see how I get my video on.
Awesome. Thank you so much, Jeremy. Cool. So we have about 15 minutes for questions. Feel free to just come off mute, or if you're more comfortable, you can type your question in the chat, and I'm happy to read it out for you as well. Yan, see you raise your hand.
Yes, maybe to break the ice. Thank you so much for the presentation. I'd be curious to hear what are you looking for in terms of feedback? What kind of feedback are you looking for in the coming months for the preprint?
Yeah, that's a great question. We've got a lot of good feedback from different directions at this point. Some have gone really off into the weeds on the statistical testing stuff, which has been great, but maybe for the kind of understanding revisions we need to make to go to JSIM, it'd be really good to know kind of the practicality of implementing a lot of this in your workflows. If you kind of see a major limitation in the implementation of statistical testing, we've already gotten a number of feedback that kind of it adds a lot of computational complexity. The metrics that we're recommending, some people prefer other metrics. So just how this works within your workflow, and if you see kind of major wrenches in what you're doing, that would be good to know about.
Hi, yeah, I have a bit of a forward-looking question for your data set splitting, because it does ultimately tie in with this. I know we've only talked about random today, but my personal research, I'm very interested in alternatives to that. So you alluded to clustering and then partitioning based on that. I think that's a really interesting approach forward. I think, how does that play with the suggested repeated cross-validation that we have here, especially in light of your comment about how getting the rigorous fold sizes correct can be a little bit of a challenge?
Yeah, so I think with scaffold splits or chemical clustering, that should all fit pretty naturally into repeated CV. Even in the examples that we did in the paper, we did it was a scaffold split. I think it was like a Bemis Merco scaffold split. So as long as the fold sizes aren't kind of insanely different in size, you don't have like extremely small folds, models should, or the approach should be robust to changing sizes of folds that typically are induced with chemical clustering. So I think it should plug in pretty naturally to that. We've seen that so far. But one of the advantages of this repeated CV approach is it's pretty easy to extend to different splitting methods. The only one that's kind of come up where there's some complexity, and we'll go into that into this next paper, is doing a time split. But this paper is more focused on benchmarking and public data sets that are used in the literature. And usually those don't have timestamps. You'll do something like a chemical cluster split. But yeah, we plan on talking about in this next paper, kind of handling time splits that would be more relevant to industry.
Yeah, I really appreciate that. And great work in general, too.
Thanks.
Cool. Any other questions? Okay, we have a question from Sam in the chat. Can you explain the time splits a bit more? It's not obvious how time is a factor when comparing designs.
So typically the data that we have in industry, we have compounds that are being synthesized over time. And so when we train our models, we have historical data at a specific time point. And then we want to make predictions for projects as they're synthesizing new molecules. And often we have representatives of the chemical series that the teams are working on, and they're extending those series into a new chemical space. So this can be thought of as a time series data where you have a covariate shift as well. But so what people typically do in industry is to evaluate models looking at kind of historically, if you were to leave out the last month of data and then kind of move incrementally month by month and kind of do this rolling time split. And there's a nice paper by Cheng Feng, who's on our steering committee, that demonstrates doing that as a evaluation. So it's really more representative of what we're doing in industry, but there aren't data sets in the public domain that that look like that. So, so I hope I'm addressing that question appropriately. Did I get your question, Sam, or are you asking something else? Okay,
Yes, thank you.
cool.
Okay, we got one more question in the chat here. Have you thought of any possible ways for the wider community to contribute to Polaris other than providing feedback to the manuscript? Maybe I could take a first crack
Yeah,
at
that'd be
that
great.
one, Jeremy. Yeah,
Yeah, that'd
so
be great.
I mean, Polaris as a platform is fully open source, and so the idea is to make it as easy as possible for the machine learning community working in drug discovery problems to access data sets and benchmarks relevant to the modalities that you're working on. And so it's open for anyone who's interested in uploading their own data set, creating their own benchmark. We've tried to make it as easy as possible via the API to make that happen. And so we're always looking for folks in the community who are eager to contribute by, helping us add more data sets or benchmarks to the platform.
Right. Yeah, I think you covered that well. I think, yeah, you guys have a much better sense of what the collaboration will look like. Yeah, I think one of the main systems here is kind of having the steering committee put together these proposals for guidelines, and then this open feedback period to try to incorporate that feedback before we submit to a journal for publication. I think that's also kind of a main way as far as the paper writing we're looking for input. There's another one here. So do you have a protocol for preventing leakage for methods that leverage pre-training and want to evaluate on these benchmarks? That's an interesting question. Leverage pre-training. So I guess the idea there would be some of the pre-training data could overlap with benchmarks or be similar to the data that's used in the benchmarks. I haven't thought about that much as far as what we suggest in terms of guidelines. There, it would be you just have to be kind of conscious of the data that you're using in pre-training and what is available in these benchmarks. But I don't have a good answer for that, honestly. I have to think about it some more.
I also see Pat is in the room. So Pat, if there's any comments or thoughts you want to chime in before we close off the meeting as well today, feel free to share.
No, I think Jeremy did a great job of summing everything up. And just to echo what Jeremy said, any comments on the paper or on the code, please provide them to us. We'd love to get feedback.
Yeah, I'll just say the feedback we've gotten so far, it's become clear that we need to clarify a number of things in the text, that not everything was completely clear. And so it's been very helpful to get that feedback, and definitely keep that coming, because it really helps us kind of make sure that everything's understandable to this kind of broad audience that we're targeting.